In the previous video, we wrote down the finite precision version of the encoder for arithmetic coding, and now we're ready for the decoder. So let's do it. All right, so this is going to be the decoder, finite precision. And similarly to in the infinite precision case, we will have the following input. So the output from the encoder was this binary sequence, the encoded sequence. And we're going to get that sequence, and there may be some other bits at the end also. So if you remember back to when we talked about this in the infinite precision case, the decoder, it's not just necessarily going to get this sequence on its own, it's going to get that sequence plus some other bits. You know, those other bits could be like additional messages that have been concatenated onto this one, or they could just be, it could just be that this is stored in memory somewhere, and you have to know where your file ends. And if that's not given to you ahead of time, you're not given this M, you're not given the length of this encoded message. You have to figure that out. And part of the responsibility of the decoder is figuring out what M is so that you know where your file ends. Okay, so we get that, and we also get our C, just like before we get our C and D, and let's suppose we also get this R once again, like in the encoder. Very good. So now, similarly, so this is going to start out looking like the infinite precision decoder. We initialize A to 0 and B to whole. Whole is playing the role of the number 1. And now let's initialize Z before we initialize this to the binary number corresponding to this sequence. But now let's initialize it to 0, and we're going to approximate that binary number. So Z starts out at 0, and I is going to be a counter, an index into this array. Then we'll start that out. Actually, we'll start at 1. So the first part of the finite precision decoder is initializing Z to an approximation of that binary number. So here's how we're going to do that. Here's one way to do it. So we'll do a little while loop. While I is less or equal to precision, so we're going to use precision number of bits for our approximation. While I is less than precision, and we don't want to overrun M. So M, M could be an upper bound on this little m, or it could just be, if you're not given an upper bound, if this is like an infinite sequence, then you would just drop this condition. So big M is just some upper bound on little m. Okay, so we're going to do this loop, and we're going to, at each iteration, if beta I is 1, then we increment Z by 2 to the precision minus I. So we're constructing this binary number Z, and then we increment I. So basically, all this is doing is initializing. So this is basically initialize Z to be the number beta 1 up to beta precision in binary. And note that this is an integer now. I'm not using it's not a binary expansion. There's no point here. This is an integer. Okay, so that's our initialization, and we're going to update Z as we go. We'll do that below. Now we're going to have a for loop, similarly to, or not a for loop, excuse me, a while loop. Similarly to before, we had the infinite while loop, and we're going to decode a symbol at a time. So here's what's going to happen. This is going to look similar to the infinite precision decoder for j equals 0 up to n. So we're going to consider each possible source symbol as the next possible symbol to be decoded, and we will do the following operations. So like in the infinite precision case, we set W to be B minus A, and we consider the B and A corresponding to that next possible symbol. But now we're doing integers. So remember, just like in the encoder, everything is in integers here. So this is going to be the exact same rounding operation that we did in the encoder. So however you implemented this, you're going to do it exactly the same way here. Exactly the same way. Round W CXI divided by R. Oops, that's not supposed to be. I'm so used to writing the encoder version. This is J. Excuse me. We don't know what XI is, so this is J. And then, just like, once again, in the infinite precision algorithm, we're going to check if that is indeed the next symbol. And how do we check? We just see whether the current Z is contained in this interval from A0 to B0. And this is slightly different than the infinite precision algorithm. I mean, it's written exactly the same, but remember that Z here is just an approximation to the true Z. It's supposed to be defined to the true Z. So, but it's the best possible approximation that we can make with our given level of precision. It uses these this precision number of bits. All right. So in this case, what we do is we update our, well, first we emit J, because we know that that was the next symbol. J was the next symbol to be decoded, because it was contained in that interval. The interval corresponding to J contained Z, so we emit J, just like before. And right. Oh, and then we update our A. Our new A is A0. That was the correct new A. And our new B is B0. And we have to see if we're at the end of the file. So we check, is J our end of file symbol? 0 is our end of file symbol. If J is the end of file symbol, then we quit. Finish. So this is when the decoder can terminate. But now we're not quite done yet. This was when we finished the infinite precision decoder. But now we have some more work to do because we need to integrate those rescaling operations into our decoder. All right, so let me first indicate here. This section of code was decode next symbol and update A and B. Now, the next step, the next part of the algorithm, or the last part of the algorithm, is those rescaling operations. And this is the crucial part of the decoder. And it's tricky to get it to work, but I'm going to show you how to do it. So the key thing here is to rescale and round in exactly the same, so the key is to rescale at exactly the same times during decoding as you did during encoding for the particular sequence that you have. So this is so important that I'm going to write rescale at exactly the same times, the same points in the sequence, so that when you do this rounding, you get exactly the same values of A and B at any given step in the process. So that when you do this comparison, you get exactly the same result. Exactly same times during decoding as during encoding. So rescale at exactly the same times and in exactly the same way. So here's one way to do that. So remember that above, let's go back to our encoder here. In the encoder, we were going through this for loop, and we had, we computed the new A and B for the next symbol, and then we did these rescaling operations. So we're going to mimic this process during decoding. So during encoding, we went through this loop some number of times, one time for each source symbol encoded, and depending on what A and B were, we rescaled at certain points. And so we're going to do that rescaling, just like I said, in exactly the same way and at exactly the same times during decoding as during encoding. So let's do it. So here we go. So what color should we use? Let's use this orange. While, so no, not in that for loop, excuse me. So we're in this while loop here. While, maybe I should indicate where these loops are going. This is the for. This if contains this stuff. Okay. And this while, this outer while here is going to contain all this more stuff to go. Okay, so now we have, after we determined the next symbol and we updated A and B, we're now going to do some rescaling. So we're going to do it in exactly the same way. While B less than half or A greater than half, we're going to do possibly cases 0 or 1. So in case 0, and if B is less than half, then we update A and B just like we did above. A is 2 times A, B is 2 times, B is 2 times B. And now we also need to update Z, right? So we also need to update Z. We need to keep that in the right relationship to A and B. Z becomes 2Z. Otherwise, if A is greater than half, then we're in case 1, and we update in the same way that we did above. A becomes 2A minus half, B becomes 2B minus half, and Z becomes 2Z minus half. So we're keeping Z in the same relation to the others. Now, remember that Z was an approximation. When we initialized Z up here, we started out as 0, and we initialized it in this way. And Z was just an approximation to our given level of precision. So when we do this rescaling, think about what's going on here. So we're blowing things up again. So when we multiply Z times 2, we're basically like left shifting that binary representation here. So if this was a 0, so that's the case where B is less than half. That's the case when that first bit was a 0. Well, the first bit is going to be 0 in that case. That's not exactly when that happens. But the first bit is going to be a 0, and this operation basically just left shifts this binary representation. And similarly, in this case here, if A is greater than half, then the first bit of our approximation to Z is going to be a 1. So this half is subtracting off that 1, and then the 2 is left shifting it, basically. That's the way you can think about it. So what we need to do after we do those rescalings is we need to update our approximation of Z. So let's do that. So let's update that approximation. And here's how we're going to do that. So if we're not yet at the end of our binary sequence, and the next bit in the sequence is a 1, then we should update Z to reflect that fact. So then we set Z, the new value of Z is Z plus 1, right? Because Z is this binary thing, and after we left shifted it, there's this last bit that we need to read off, the next bit in the sequence. It's not going to be beta precision, it's going to be beta I at this point. So this is going to be beta I at this point in the algorithm, the last bit of Z. And after we do that, we should increment I, because we've read off that next bit from our sequence of betas. Very good. And now we have to do the other type of rescaling. This was when we were in the lower half or the upper half, And we have our quote-unquote middle type of rescaling that we have to consider. So if a is greater than quarter and b is less than 3/4, or 3 times quarter, then we need to do the middle rescaling type of step, and that's just the following. So a becomes 2a minus quarter, b becomes 2b minus quarter, and z becomes 2z minus quarter. Z, 2z minus quarter. So just as a reminder, I'll just go back up here to remind you. So this was in the encoder. This was our rescaling. And so here, during decoding, we're rescaling in exactly the same way. So in this middle rescaling step, if a is bigger than a quarter and b is less than 3/4, then, well, we had to increment s before. We don't need to worry about s anymore. We don't need to worry about s, but we do need to rescale in exactly the same way. And we have to update z as well. All right. Whoa, what happened? Oops. Okay, there we are. Back to our decoder. And similarly to before, in this, if we do this rescaling, then we've shifted z, and we need to update our approximation. So for every iteration through this while loop right here, we need to update z. So if I is less than m, and so this is exactly the same as what we did above, and beta is 1, then add 1 to z, and increment. We're always going to increment I. So I is going to keep track of how many times we've left shifted z. Okay, and let me now indicate, just like to be consistent, I'll indicate the nesting structure here. And that is going to do it for the decoder. That does it. So that big while loop out here, this while 1, and each iteration of that while 1. So maybe just recap here. So this is our decoder. So we initialized z to this approximation, to this binary number, and then we went through this while loop, and on each iteration we decoded the next symbol by looking at our current approximation to z, and we emitted that symbol, and we updated a and b, and if we hit the end of the file symbol, then we quit. And then we also did these rescaling operations to ensure that at each step, at each iteration, when we get to this point, that our a's and b's are exactly the same as they were during the encoding process. That is so critical. Okay, you're getting tired of me saying that, but it is really important. And so we did this. And now the output of this whole thing, so we have the output. Let me put that. Output is the original sequence that was encoded, x1 up to xk, and, or in other words, it was the original source sequence. I'll put it this way. So to be clear, so what I mean by this is the sequence that was emitted during this algorithm, which it coincides with the original sequence, of course, because we decoded it. All right, so that is our decoder, our finite precision decoder. And one last detail to mention here, to explain, is how to get m. So remember I said at the beginning that the responsibility of the decoder is not only to decode the message that the initial part of this binary string represents, but also to tell where that binary string ends. So you need to figure out what m is in general. You may need to figure out what m is. And so I'm not going to write down algorithmically. I'm going to leave it as an exercise for you to figure out if you are interested in wrapping up that detail. But I'll basically indicate the rough idea of what you do. The rough idea is that you're going to look at z, your current representation of z, at the termination of the algorithm. And it's going to be something like, it's going to be something like if beta 1, so this is determining m. So if we had beta 1 up to beta m plus 1, beta capital M, then your final z is going to be somewhere, it's going to be some binary sequence that's some subset of these, some substring of this right here. So z is going to be somewhere here. And a and b are going to be, some integers that whatever they happen to be at the end of the algorithm. And what you're going to do is similarly to the, to in the infinite precision case, you're going to find the first, the first few, however many bits of this initial part of z. So if z is z1 up to z precision at the end of the algorithm in binary, so these are, each of these is a bit, each of these is zi is a bit, then you're going to find whatever the initial sequence, z1 up to zi, and then zeros, so that the interval corresponding to this number is contained in the interval from a to b. Well, I shouldn't put I here. Let me put j. Because I is going to help you determine what m is. Because remember that I was keeping track of how many times we left shifted a, b, and z. So I is going to tell you where the end of your z occurs with respect to m. So you're going to use z, a, and b, and I to determine m. And I'll leave that detail to you. Okay, so that is the decoder. We did it. So that finishes our description, our description of the finite precision arithmetic coding decoder, and I'll iterate at the expense of being monotonous that the key thing here was to rescale at exactly the same times during decoding as during encoding. Okay, so we finished our description of the finite precision encoder and decoder, and this was quite a long section overall about arithmetic coding, but it's truly a remarkable algorithm. I hope you'll agree now that you're familiar with it, and hopefully you'll have a chance to implement this algorithm and see for yourself how amazing its performance is. And maybe you can even play around with some non-IID models, and maybe you could even break some of the world records for compression performance. Some of the best performing algorithms, or the best performing compression algorithms, use arithmetic coding. So maybe you can break the current world records, implement the algorithm and implement a good probabilistic model of language or different sources that are real world sources, and maybe you can be the next one to have the best performing compression algorithm. Okay, happy coding, and I'll see you next time.